Okay, I can start. And probabilistic combinatorics webinar. I want to draw your attention that this seminar is recorded and will be put on the internet, so bear this in mind when asking questions. There will be also an informal session at the very end without being recorded. So if you are shy or you want to ask more informal question, you can wait to the end. Mehtaab is very happy if you just interrupt him with questions in the middle, or you can also use the chat, and I will draw his attention to the questions. The slides are on our webpage. I will send the link in the chat. If you want to go backwards to some definition or so. So it's my pleasure to introduce Mehtaab Sawhney, who will be talking about local limits theorem for subgraph counts.
Thank you so much for the introduction. Hopefully everybody can hear me okay, and thank you for the invitation. So today I'll be talking about local limit theorems for subgraph counts, and this is all from joint work with Ashwin Saw, also at MIT. So I'll begin by sort of discussing the distinction between central limit theorems and local central limit theorems. So here I've drawn two different probability distributions. So the first is I had my computer simulate 500 1,000 coin tosses and count the number of heads. And the distribution shown is the sum total of the number of heads. And so it's a normal distribution with mean at 500. And in the second, I counted the number of heads, and based on what the number of heads was divided by 3, I added some small perturbation. So while in both cases you have at a global scale a central limit theorem, the probability distributions here, if I look pointwise, they obviously look very different. The first one is much more regular than the second one. In particular, this distinction between the local and In particular, this distinction between the local and in particular, this distinction between the local and global behavior will be, somebody has a question?
It's not a question, it's just the link of the slides.
Oh, sorry. And so while the first distribution both distributions exhibit a central limit theorem, the first exhibits a local central limit theorem, while the second does not exhibit a local central limit theorem. And that distinction will sort of be the critical distinction throughout the talk. So more formally, let's define what it means for a sequence or set of random variables to satisfy a central limit theorem, just for the sake of concreteness. So I have a set of random variables xn with means mu_n and variances sigma n squared. We say they satisfy a central limit theorem if for every two real numbers a and b, the probability that the normalized random variable xn minus mu_n over sigma n, the probability that's between a and b, approaches what that probability would be for a standard Gaussian or a standard normal random variable. And note that this is a purely distributional statement. What I mean by that is that we're fixing two real numbers, a and b, and then sending n to infinity. So this only gives you control on the probability that your random variable xn lies in intervals on scales proportional to the standard deviation. So you're not controlling the probability that xn lies in intervals of length square root of sigma n, at least just given this limit definition. Now, if you have a more precise control on the limiting behavior, your error term might give you slightly better control. But what we'll be concerned with is sort of much more precise control, in particular like pointwise control. And this motivates the definition of a local central limit theorem. So for when we'll be discussing local central limit theorems, all our random variables will be integers. So consider a set of integer valued or integral valued random variables xn with means mu n and variances sigma n squared. We say they satisfy a local central limit theorem if this rather funny expression holds. So what is this saying? So naively, if you imagine drawing your bell curve, you can have a naive guess for what the probability that xn equals a particular value x is. What you do is you draw your bell curve, you look at the point where xn equals x, and then you take you basically integrate a strip of like length 1 because these are integer valued. And so you would naively expect that that point probability is accounting for that interval of length 1 in your Gaussian. And if you do the calculation, what that is you're integrating over a scale of length 1. And if you calculate it, you get this expression 1 over sigma n square root 2 pi x of minus mu n squared over 2 sigma n squared. And this is just basically the expression for a Gaussian. And the key point is now I take the supremum over all values in Z, and I say that that difference is going to tend to 0. Now, so the first key thing to note in this definition is that instead of looking at the probability that xn is lying in certain ranges, in particular before we were looking at ranges of the scale of the square root, the scale of the standard deviation of the random variable. Here instead, we're looking at the point probabilities. And the second thing is this scaling. So I mentioned it once, I'll repeat it again just for the sake of concreteness. Why am I looking at the scaling of sigma n times the probability that xn equals x? So roughly, if xn is satisfying a central limit theorem, you know that the probability that it's within one standard deviation of its mean is some constant. It's 0.68, I think. 0.68 up to 2 decimal places. And so this, let's say 2 sigma n interval around the mean has some constant amount of the probability mass. And so you naively expect that each point in this interval, and there are 2 sigma n integers in this interval, would have an roughly equal proportion of the mass. So you're splitting a constant 1 over sigma n values, so each point probability is roughly 1 over sigma n. And that's why you're getting the scaling of sigma n times the probability that xn equals x. And that's accounting for this first term in the expression. So local central limit theorems have a long history, and sort of I'll give a very, very brief overview. So the first central limit theorem, the Dumois-Laplace central limit theorem, was in fact a local central limit theorem. So what Dumois and Laplace showed is that they showed that you take a sum of Bernoulli random variables, then they satisfy a central limit theorem, independent Bernoulli random variables. And if you look at their proof, it's actually just proving that every point probability is correct. So in fact, it's proving a local central limit theorem. The first sort of general local central limit theorem was due to Gdańko, who proved that sums of independent integer valued random variables subject to obvious constraints satisfy a local central limit theorem. And let me be a little bit more explicit about what these obvious constraints are. So if I'm looking at a set of integer valued random variables, I'm looking at a random variable x, and I'm taking many independent copies and summing them. If x, for example, was always even, then there would be a problem because the sum would also be always even. And therefore, I don't get a local central limit theorem over the integers. Maybe I get over some sublattice, but not over the integers. And the obvious constraint is that you don't lie on some sublattice of the integers. And that's how you get a local central limit theorem. And that turns out to be the only condition that you need if you're taking independent copies of the same random variable. And by now there are numerous examples of local central limit theorems in combinatorics. One particularly incredible result was due to Bender, Kenfield, and McKay, who showed that the number of vertices in the giant component of in the giant component satisfies a local central limit theorem. In fact, they get something slightly stronger, where they can do both. They can show some sort of local limit theorem for the number of vertices and number of edges. And this was improved to hypergraphs later. So stepping back for a moment, our eventual goal will be to prove local limit theorems for subgraph counts. And it turns out the first directions in this result, sort of in the dense case, amount to proving results regarding the equidistribution modulo fixed prime skew. Obviously, there's critical work of actually proving a central limit theorem for subgraph counts, but I'm going to start the story here. So the first result in this direction was due to Lobel, Matuszek, and Pongrak, and they proved that if I sample a random graph in Gn1/2, that the number of triangles is equidistributed modulo any prime q as n tends to infinity. So more informally, if I sample a graph in Gn1/2 and then count the number of triangles, the probability that's even or the probability it's odd will be a half as I take n to infinity. And the reason they were interested in this is that it's very easy to see this basically because I can prove this for any fixed prime q, I can take a slowly growing function of q. And what this proves is that for almost every pair of random graphs, they don't have the same Tut polynomial, and that was their motivation. This was extended by Colodis and Kopparty, who proved that if I look at any connected graph H, and then I look at the number of copies of H in GNP, that's equidistributed modulo any prime q as n tends to infinity. Here I'm fixing p and sending n to infinity, so I'm considering a dense graph. And they showed that this equidistribution holds for any connected graph H. In fact, they demonstrate a much stronger statement. What they show is that if I take a set of connected graphs H, H1, H2, H3, ... and then I look at the joint distribution modulo Q that's equidistributed over all the possibilities. So this is some joint equidistribution result. And these may seem pretty far away from something like a local central limit theorem, but sort of as the example on the first slide showed, there's actually a close connection. And this is strong motivation for the truth of a local central limit theorem, because it establishes there are no mod biases. So if it turned out that the probability that you have an even number of triangles is much higher than that you have an odd number of triangles, this would tell you that a local central limit theorem couldn't hold. And results like this are guaranteeing you, okay, that obstruction is not occurring. So while this is not sufficient for proving a local central limit theorem, it's definitely a necessary prerequisite. And so that's why it's important for our considerations. So the first general result towards proving local central limit theorems was a local central limit theorems for triangles. And this was due to Gilmer and Kopparty. So what they proved is that if you fix p in 0, 1 and let xn denote the number of triangles when you sample a random graph G from GNP, then it satisfies a local central limit theorem. In particular, if I let mu n equal the expectation and sigma n squared equal the variance, you have that sigma n times the probability that xn equals x equals this expression. And if I take the soup over all integers. So this is exactly the definition of a local central limit theorem before, and they proved the truth for triangles. And this is roughly proved by a Fourier inversion argument on lattices, along with decoupling inequalities. And we'll return to this general setup as it appears in all the later works on this problem as well. This was then extended to Cliques by Berkowitz. So in particular, he showed that if you fix p and an integer k, and you let xn be the number of k cliques in GNP, then you have a local central limit theorem for this random variable xn. In fact, he showed another result, which is incomparable, but very close. He also showed another result, which is in principle incomparable, but in reality, usually a little bit harder to show. What he proved is that if I look at the probability that xn equals x and subtract its expectation, and then I sum over all integers, this difference tends to 0. So there's a difference in normalization here that I'll briefly explain. So what happens is that the probability that xn equals x is something of order 1 over sigma n, and the Gaussian is roughly supported on sigma n values. So what you need to show is that each term is little o of 1 over sigma n. And this is very closely related to proving a local central limit theorem. In particular, what this is actually saying sort of more heuristically, is that if I look at the random variable that's counting the number of k cliques in GNP, that if I look at the TV distance between that random variable and this discrete Gaussian random variable, that TV distance tends to 0 as I tend n to infinity. So it's in some sense really confirming what you think of this random variable as basically just being a discrete Gaussian. And throughout this talk, I won't be stressing this point of sort of a point-wise local central limit theorem versus the sort of TV result. But basically, it's because this result follows as soon as you specify a sufficiently strong error term in your local central limit theorem. And this was a distinction between the work of Gilmer and Kopparty and Berkowitz, in that the earlier work was not able to give such a TV bound, while Berkowitz's result gives it essentially for free. Finally, before stating our results, I'll bring in another perspective, and a perspective of anti-concentration that's been brought to the problem. So anti-concentration broadly refers to giving upper bounds on quantities such as you have some random variable xn, the probability that xn equals x, or that the probability that xn lies in some interval between x and x plus y. So the first quantity is giving an upper bound on the maximum point probability, while the second quantity is giving an upper bound that your random variable lies in some interval of length y. And this name anti-concentration stems from the fact that these quantities upper bound the maximum point probability, or upper bound the probability that the random variable is localized to some interval. So in concentration, you're trying to see how close you are to the mean. Here you're saying you're not exactly the mean very often. And hence the distinction between concentration versus the name anti-concentration. And anti-concentration is an especially broad and rich topic, especially like in the interplay between this and random matrix theory, going all the way back to even like the first results regarding singularity of Bernoulli random matrices due to Komlosh. This distinction, this connection was already established, and it turns out to be a very rich connection. And for the remainder of the talk, we'll be restricting our concern to when xn are the random variables, are basically subgraph counts in GNP, but that's really not representative of anti-concentration as a whole. And the motivation for this question regarding understanding anti-concentration of sort of polynomial functions of Bernoulli random variables has other applications more broadly. So the motivating conjecture in this direction is a conjecture due to Fox, Kwan, and Sauermann. So here, as usual, fix a knot P in 0, 1, and let H be a graph with no isolated vertices. The reason you need to exclude isolated vertices is that if you have an isolated vertex and you're counting copies of your subgraph H, the isolated vertex can basically go in n minus H position, n minus the number of vertices of H positions. If you look at the subgraph H prime that is connected, and then if you have one additional isolated vertex, this vertex can go anywhere. So you sort of get a trivial divisibility in the number of counts. So this is a sort of obvious condition for needing the correct anti-concentration to hold. And let xh count the number of copies of H in GNP, and let sigma H be sigma h squared be the variance of xh. Then what they conjectured is that the maximum point probability of xh is bounded by 1 over sigma h, up to a constant depending on h. And this is sort of the best possible for sort of up to the constant for the naive reason that you know this random variable satisfies a central limit theorem. And since it satisfies a central limit theorem, you know that, as before, that the probability that you're within one standard deviation of the mean is some constant. So at least one of the values within one standard deviation of the mean has this probability. And so you're saying, this anti-concentration conjecture is saying, it's not much larger than that trivial bound I just gave. And this was motivated by anti-concentration results of Mecca, Nguyen, and Vu. They were concerned with sort of understanding anti-concentration bounds for polynomials of Bernoulli random variables, and their results, for example, showed that for any graph for any graph H with no isolated vertices, each point probability is bounded by n to the minus 1 plus the little 1. The little 1 is hiding log factors. Furthermore, this connection between local central limit theorems and this anti-concentration result is in some sense, the local central limit theorem is strictly stronger in that the local central limit theorem of Berkowitz immediately implies this result for Cliques. And in the same paper, Fox, Kwan, and Sauermann showed that this is true up to a small multiplicative factor. In particular, let xh be as before, and let h be a connected graph. So not on the hypothesis that h has no isolated vertices, but on the stronger hypothesis that it's connected, that the maximum point probability is n to the little 1 over sigma h. So basically, they lose a subpolynomial factor. And given that sigma h is polynomial, this is essentially the conjecture, at least for connected graphs h. So now I'll state our main result. Our main result is a local central limit theorem for subgraph counts of connected graphs H. So in particular, the same setup as before, fix a P in 0, 1, and let H be a connected graph. Let XH denote the number of copies of H in G and P, and mu H and sigma H be the mean and standard deviation as before. So then you have that XH satisfies a local central limit theorem. In particular, the first expression is true, and furthermore, our error term is strong enough to give this notion of the TV distance between the random variable xh and a discrete Gaussian. Furthermore, we prove a number of extensions of this result. You can sort of prove an analogous theorem for induced subgraph counts. So here there's an additional restriction. So you can count induced subgraph counts of any disconnected graph H, but you need the additional restriction that this probability P you're considering is not in some set of critical densities P sub H. Furthermore, we can extend both of these theorems to the GNN model. So here, instead of sampling each edge with probability P, you're choosing a random graph where you have exactly M of the n choose 2 edges. And M here is chosen so that M over n choose 2 is a fixed constant. So in particular, we're always going to be dealing with dense random graphs. And note in this case that the underlying set of random variables is no longer even independent. So that presents significant challenges. And finally, we prove a local limit theorem, but not a local central limit theorem for KAP counts in Z mod NZ. So what the model is, I sample each element of Z mod NZ with probability P, and then I look at the number of K-term arithmetic progressions. And here's co-prime to K minus 1 factorial for just concreteness reasons. And the key point is here, the limiting behavior is actually much more complicated in discrete Gaussian. So in particular, in direct work with Saw and Berkowitz, we proved that this random variable does not have a local central limit theorem. And instead, the behavior is slightly more complicated. So let's just briefly walk through the graph here. So this graph shows I took a bunch of samples of Z mod 101Z. I took each element with probability 1/2, and then I counted the number of 3-term arithmetic progressions. As you can see, there's a wildly varying distribution. In particular, while this random variable on a global scale satisfies a local central limit theorem, on a local scale, it sort of obviously doesn't. This distribution is far too irregular. And what we can show is, what is this irregularity exactly? Now, for this part of the talk, I'll briefly give a high-level proof sketch of the results. And for the sake of simplicity, I'll focus on proving a local central limit theorem for subgraph counts, and mostly even for the case of just triangles, and what are the main ideas. So the first observation, sort of going back to basically work of Gdenko, is one way to prove a local central limit theorem is to do Fourier inversion on lattices. So in particular, if you let ZH denote the normalized version of XH, so in particular, XH minus mu H over sigma H, it suffices to prove that the characteristic function of ZH is approximately the characteristic function of the Gaussian random variable, as long as you look at heights t between where the absolute value of t is less than pi times sigma H. So stepping back for a second, if you wanted to prove a central limit theorem, it suffices to prove this when t is a constant. This is basically the content of Levy's continuity theorem. So, so instead of proving it for a constant, we now need to push t all the way up to pi times sigma H. And so this is a very different statement. You're somehow controlling the characteristic function at much, much higher frequencies than what you have to control to prove a central limit theorem. And it's not just this tilde approximation you need to show. You actually need to show that, or one necessary condition to prove a local central limit theorem is that if I take the integral of this difference between minus pi times sigma H to pi times sigma H, that vanishes. That tends to 0 as n tends to infinity. And basically, however good your bound is on this integral immediately translates to a bound on your error term in your result for your local central limit theorem. So the strategy broadly is to break up this integral into different sizes, into different pieces based on the size of t. So the first part is when t is relatively small. So for t less than n to the epsilon, you're essentially asking a distributional question. In particular, the function x to e to the itx is basically a t Lipschitz function. And in this range, you can sort of just use distributional techniques. In particular, for GNP, Berkowitz observed, but I'm sure this observation is older, is that if I look at x sub h, so for concreteness, let's just look at triangle counts. The variance of this random variable in GNP is basically determined by the number of edges. So if I tell you the number of edges you sampled in your GNP and no other information, you can make a much better guess for the number of triangles in your random graph than just if I told you it was sampled from GNP. And this observation, along with any proof of the central limit theorem Barry has seen, I think is more than enough. You can obtain a sufficiently strong bound in this regime. For GNM, you run into a more complicated issue. The reason is the random variables are no longer even independent. And this observation in the first case that you're largely determined by the number of edges is no longer true. And what you need to use is sort of a Stein method argument. In particular, you use exchangeable pairs along with some transference. This is very closely related to work by Barber, Kruczynski, and Ruczynski on their work of quantitative central limit theorems. I should note here and be explicit that it was known that x sub h in GNM satisfies a central limit theorem. This is essentially in work. It's explicitly stated in work of Janson, but it's over many different papers. So finding this particular statement is a bit tricky, but he proves a far, far more general result. But we need a very quantitative result, and basically we prove against all t Lipschitz test functions. And a result of that form was not stated in the literature, to my knowledge. The more challenging case turns out to be higher frequencies, or when the absolute value of t is bigger than n to the epsilon. And in this case, you need to use a combination of decoupling, and just Cauchy-Schwarz a bunch. So the high-level idea is that you're looking at e to the I t zh, and zh is some relatively high-degree polynomial. The way you reduce this is you apply Cauchy-Schwarz a bunch, and you try to reduce this to understanding the characteristic function of a lower-degree polynomial. In particular, hopefully it's a linear polynomial, and we know how to handle linear polynomials very well. And roughly, this is similar to something like van der Korpitz inequality, or in physical space, or this is very closely related to, for example, why you would define the Gowers norms. And note that this is, for very high t, this actually becomes very similar to the problem mentioned about understanding equidistribution modulo small primes. So in particular, let t equal pi times sigma, then this characteristic function, e to the I t zh, a simple computation shows that basically this is the expectation of -1 to the x of h, where x of h is counting the number of number of copies of h as before. And we need this to be small. And when is this expectation small? This expectation is small precisely when the subgraph counts modulo 2 are approximately equidistributed. And thus for very large t, in particular where t is bigger than sigma h times n to the minus epsilon, this is basically, it's very closely related to earlier results on equidistribution modulo primes. And sort of the same techniques work in this regime. And therefore, the most technically involved cases stem from understanding when you're between n to the epsilon and sigma h times n to the minus epsilon. So this intermediate range of t. So to provide one concrete example of decoupling, I'll walk through an example given by Berkowitz, and this sort of allows you to essentially give a full proof of the local central limit theorem for triangle counts. So fix your set of ground vertices, fix your set of vertices n, and split them into two parts. U1 will be from 1 to n over 2, and U2 will be the remaining vertices. Now we can construct two edge sets, B1 and B2. So the edge set B1 is just the set of edges with both vertices in U1, and B2 is the remaining edges. And finally, let y and z just be the indicator vectors of these two subsets. Since we're going to focus on triangles, the key idea is to sort of rewrite your random variable as a sum of three parts. You write it as a of y plus b of z plus c of yz. As stated, this means nothing, but you can sort of interpret this to be a of y counting the number of triangles where all three of your edges are in B1. And this is equivalent to having all three of your vertices in U1, or the first half. B2 counting triangles with all edges in B2. And CYZ counting triangles with one edge in B1 and two edges in B2. And it's easy to see sort of if you draw the picture that you can't have two edges in B1 and one edge in B2. This is just by the construction of how we defined U1, U2, B1, and B2. The key point is this 4-line Cauchy-Schwarz calculation, and let's walk through it step by step. So here we're considering the characteristic function of e to the it xk3. So just writing out the random variable as ay plus bz plus cyz, we get that this is the expectation over y and z of e to the it ay plus bz plus cyz. So the first idea is we have this term a of y that only depends on y. By using Cauchy-Schwarz, I can just sort of throw that away. And so by Cauchy-Schwarz, this is upper bounded by the expectation of y times the absolute value of the expectation of z of e to the it bz plus cyz squared. And so at a first level, we've checked out one of the terms a of y. So now you have this expectation of z e to the it squared. You do the only thing you can. You expand out z in terms of two independent copies, z1 and z2. And so you get e to the it bz1 plus cyz1 times its conjugate, which is just minus bz2 minus cyz2. Now I have two expectations, the expectation of y, the expectation of z1, z2. You do the only other trick and you swap the two terms. So then you get the expectation of z1 and z2 of e to the it bz1 minus bz2 times this expectation over y. Finally, you just apply triangle inequality, and you get that this is upper bounded by the expectation of z1, z2 times this expectation of y, e to the it cy z1 minus cy z2. So this is a little bit of a non-trivial calculation, but the key point is, first note that we've eliminated these terms a of y and b of z, and now we're sort of left of bounding this characteristic function of c of y z1 minus c of y z2. And note that at first sight, what did I gain, right? Because in this decomposition, c of yz was the most complicated term. It was the only one that depended on y and z both. But recall that c of yz counts triangles with exactly one edge in B1 and two edges in B2. And note that y was the indicator function of B1. So this is a linear polynomial if I look at it as a polynomial in y. So fixing z1 and z2, since it's a linear polynomial in y, we can understand it very well. And you just use independence, and it's pretty easy to handle. So this problem reduces to showing that for most random choices of z1 and z2, you can show the necessary cancellation in this characteristic function. And this is basically the key point, because originally we had some degree 3 polynomial we weren't able to handle. And this combination of, this is basically decoupling. By decoupling, we're able to reduce it down to understanding a linear polynomial. And that's what you've gained through this computation. So this analysis plus a little bit more work basically recovers the results by Gilmer and Kopparty regarding local central limit theorems for triangles. And even for cliques, Berkowitz needed more non-trivial decoupling techniques. In particular, the key problem happens that in the above case, we're able to reduce from our general polynomial to something that was a linear polynomial. In particular, c of yz1 minus yz2 was a linear polynomial in y. In general, you won't be so lucky. In particular, what you'll get instead is you'll get the final polynomial is in some sense dominated by the linear term. I don't want to be more precise, but it's some like Fourier theoretic sense. And sort of figuring out how to handle decoupling for polynomials like this is sort of the key insight of Berkowitz. And roughly the idea is you use some Taylor expansion plus hypercontractivity to show cancellation in these cases. And for our extension, first, in extending this to all graphs, there's significant complications, but the main difficulty is even extending, the other main difficulty is when you try to extend this to GNM, you no longer have independence among the underlying random variables, and even linear variables among your set of variables don't necessarily exhibit cancellation. So what I'm saying here is that if you have GNM, you have indicator variables for each of the edges. If the linear polynomial whose characteristic function you want to control is basically the sum of the random variables, you're not going to get any cancellation because you already know the sum. And sort of adapting arguments to sort of handle this case, along with being in a more general setting, is basically the technical meat of the paper. So now, I previously said that our local central limit theorem was proved for all connected graphs H. It's sort of natural to conjecture that, in fact, it would hold for all graphs H. This, in fact, turns out to be false. This was known before, but in fact, an even stronger thing is true. Even anti-concentration is false. So in particular, the conjecture by Fox, Kwan, and Sauermann is not true. And the counterexample is you fix the graph H, that's the disjoint union of two edges, and fix P in 0, 1. Sample G as before, and let XH count the number of subgraphs of G isomorphic to two disjoint edges. And note here that I'm counting subgraphs and not homomorphism counts. And what you can show is that the maximum point probability is n to the 1/2 times sigma H inverse up to some constant. And this is n to the 1/2 bigger than what you would expect. Furthermore, a restriction, there was this result I had mentioned regarding induced subgraph counts. and you needed your probability P to be away from a subset of critical densities, this is also necessary. A very similar counterexample shows this is necessary. Basically, there's some explicit graph on H on 64 vertices, if you count the induced subgraph counts for GN1 half, it fails the local central limit theorem. And the proof of this counterexample actually fits on the entire slide. So there are a couple of computations we need to go through, and let's walk through them one by one. So first, for any graph H, if you sample in GN1 half, the standard deviation is of order n to the number of vertices minus 1. So since we have 4 vertices, our standard deviation will be order n cubed. Furthermore, if you sample a graph from GN1 half, the probability that you have exactly half the number of edges is order 1 over n. This follows from Stirling's formula or essentially anything. Then let's restrict to the case where I know that the number of edges is exactly half the number of possible edges. It follows from a result of Janson that the standard deviation of this random variable x of h is now order n to the 3 halves. So if I tell you that instead of being sampled from G and P, you were sampled from G and M, where M is half the edges, then the standard deviation is order n to the 3 halves. And it's asymptotically distributed like a Gaussian. So the key point now is if I take an interval of length n to the 3 halves centered around the mean of the original random variable, what you can show is that the probability that you have exactly half the number of edges is order is order 1 over n, and then you're distributing this probability mass over approximately n to the 3 halves integers, and 1 over n divided by n to the 3 halves is n to the minus 5 halves, but sigma h was n to the minus 3. So this is n to the minus 1 half, worse than what you would expect naively. And I don't expect everybody to follow the exact computation or the exact exponents. That's not the point. The key point here is that if I told you the number of edges, you got a much better estimate on the number of disjoint copies of this graph, than you would naively expect. And so this is the key issue at heart. There's no clear reason why this variance is order n cubed. In particular, nothing I said so far tells you why h being disconnected played any role in what happened. And I'll give a heuristic derivation, which is essentially the key. You can, in fact, even turn this into a rigorous proof with a bit of work. So for concreteness, let xij be a set of Bernoulli 1/2s, and let yij be the normalized version. So in particular, 2xij minus 1. And yij is a mean 0 and variance 1 random variable. So the random variable we're considering x of h is the sum over ijkl of xij, xkl, xik, xjl, xil, xjk. And basically what I'm doing here is ijkl are the 4 vertices, and I'm summing over the 3 possible matchings. Now, just substituting in the definition of yij and summing, you get that xh is 3/4 n choose 4 plus 1/4 n minus 2 choose 2 times the sum of yij plus 1/4 times this funny expression in the yij's. So note that in GN1/2, the second term has variance order n to the 6th. So the way to see this is that yij are a set of mean 0 variance 1 random variables. So the sum of yij, their n squared terms, will have variance order n squared, and you have a prefactor of order n squared. So you get n squared squared, which is n to the 4th, times n squared. So xh, if you believe all the variance is coming from the second term, would have variance order n to the 6th. And this gives you the standard deviation of order n cubed in GN1/2. So now, what is if you're doing heuristically, what is the correct, one way of saying maybe accounting for this fact that you're not in GN1/2, but instead in GNM, where m is exactly half the number of possible edges, would be just to ignore this term. Because now I know the sum of xij, because I know the number of edges, and therefore you know the sum of yij. So you can ignore the first term, and then you want to, a naive guess would just be, the variance would just be due to the second term, the final term in the expression. And so let's see how many terms there are in this expression. There are n to the fourth terms in the expression. In particular, you have yij, ykl, and you have 3 terms for each 4 tuple. So there are n to the fourth terms. And if you look at this in gn1/2 and you sort of just expand, you can show that the variance is order n to the fourth. And so this is not order n cubed, and instead it's order n to the fourth. So what happened? Where did all this variance go when I went from gn1/2 to gnn? The key point is there's basically an identity. So you can rewrite this sum over ijkl of yij, ykl plus yik, yjl plus yil plus ykj as 1/2 times this ugly expression. So what is the first term in the expression? The first term in the expression is the sum of yij squared, yij quantity squared. Since we know the number of edges, that's fixed. So that's fixed in GNN. The second term is the sum of yij squared. Yij by construction is sort of either -1 or 1. So yij squared is always 1, so that's also fixed. And then you have 2 times the sum of yij, yik. And notice here that there are only n cubed terms. So in particular, this funny expression with n to the fourth terms, once I know the number of edges, can be reduced to a polynomial with only n cubed terms. And this sort of ability to simplify the graph, to simplify the expression, is what's accounting for this change in variance. Basically, the final term, unlike the previous expression, the variance doesn't change that much from GNM to GNP. And it's an easy computation to check that the variance of this in GNP is order n cubed. And so that's explaining why I was able to simplify from order, was able to reduce the variance from order n to the fourth naively to something like order n cubed. And basically, this identity exists because the subgraph H is disconnected. And this basically, this ability to simplify disconnected components explains why they're different from connected components. It sort of explains why this distinction has been coming in throughout the talk. With that, I'd like to thank the audience for their attention. So the paper is available on the archive. Thanks for your attention, and any questions?
Thank you very much for your nice talk.